Our next presenter, Encore, a flexible modern flight software framework and development ecosystem for commercial space by Jeff Freeman and Will Maddox.
All right, thank you. Thanks for the introduction. My job is to introduce Encore and its support and ecosystem stage. Before we get started, I'm gonna lay out some prerequisites, motivation, terminology, sort of thing, and then hopefully have plenty of time to showcase two demos highlighting the features of Encore and its ecosystem. And keeping with the format of these talks, I'm gonna leave as much time for questions at the end as I can.
Sorry, I'm not. We were doing a test and I forgot to reshare. I apologize. That's your buddy's fault.
Zing.
Okay, one more time. Thank you.
All right. So yes, my name is Jeff Freeman, and I am here to introduce Odyssey Space Research's new flight software framework, Encore, and its development ecosystem stage. Before I get into the two demos I'm planning to show off, I'm going to highlight some motivation, introduce some terminology, and provided I don't talk too much, leave plenty of time for questions at the end. And as you'll see, we have a booth right outside. Hopefully the demos can turn into a bit more interactive, intimate setting if there's spirited discussion to be had. So, all right, first the obligatory elevator pitch. Encore is a modular, reusable software framework to address the needs of today and tomorrow's commercial missions. Now, I know there's probably two questions you all have. One, why is it named Encore? And that's so I can tell people I'm working on core flight software. But no, more seriously, why yet another software framework? Clearly, the frameworks of today have a proven track record of success. Well, it's this evolving commercial landscape. Safety critical, human rated commercial space stations, on-orbit servicing, that necessitated the design of a framework suited to meet those needs. Not just in terms of software design and performance, but also in terms of software testing, validation, and verification. And the list here are some of the features of Encore and its ecosystem suited to meet those needs. So let's quickly just go over them. Encore was designed to be as big or as small as you want. All that's required for Encore is a C++17 compatible toolchain with full standard template library support. If you have that, Encore lets you build software that can scale from single processor, single board computers, all the way up to complex distributed networks of computers. In its simplest terms, Encore is a loosely coupled, opt-in set of operating system and hardware agnostic interfaces. It's an application-level framework, meaning users can inject their own custom implementations or hopefully use some of the off-the-shelf provided implementations provided by Encore. The figure on the right is just a simplified view of some of the pieces of Encore. The takeaway of the figure is virtually everything in the system is extensible and customizable. The execution context, the data model, data serialization, timing, commanding, telemetry, state machines, fault detection, isolation, and recovery. I'm told the cool kids call that FITR, so I'm gonna do that from now on. All of this is there to promote rapid application development. Now, plenty of frameworks and source development kits exist promising rapid development. That's not exactly new. What is new, and at least novel, is that Encore's execution model was designed to be behaviorally deterministic. I emphasize behaviorally deterministic. What does that mean? Observable effects at the application layer follow a well-defined order. And to drive that point home, let's look at this plot here on the right, and I apologize it's small. I'll do my best to explain it. This is a very simple figure highlighting a very complex interaction of actually two separate runs of Odyssey's guidance, navigation, and control software, traversing the R-bar. Think approaching the International Space Station. One of these runs is in a simulation, software-in-the-loop environment running at 50 times faster than real time. The other one is on hardware. There are two trajectories here. They're right on top of each other. That's a big deal because despite heavy data flow, algorithmic complexity, timing requirements, the behaviorally deterministic execution model of Encore ensured the exact same results were achieved in these vastly different execution environments. So this behavioral determinism is extremely important and I deem necessary for designing good fault-tolerant architectures. Imagine how difficult it would be to design robust and reliable fitter if your software outcomes varied from run to run. Moreover, to have any kind of good degree of testing, your tests must be repeatable in order to be reliable. And you'll hear me harping on a word there, reliability. Deterministic software, behaviorally deterministic software, enables reliable software. Now, what do I mean when I say reliable software? Well, reliable software built with Encore will function as expected, always as expected, and only as expected, with the caveat to the aforementioned behavioral determinism. I'm not reaching it down into hardware and operating system specific things. This reliability is achieved by constraining the execution model in a few key ways: deterministic initialization and shutdown to safe states, the underlying state machine of the execution model running the same order every time, consistent safe data management across multiple or all the executing rate groups. Observant people might notice I'm saying the four-letter S word there, safe. Reliable software, the behavioral deterministic execution model and reliability of Encore facilitates the development of safe software. But how else does Encore encourage the development of safe software? It's built on top of a robust air handling framework. The C++17 standard gives us numerous language and library facilities to make an air handling system that's not only useful, but also safe. Things like no exceptions at runtime, outright restriction of API at runtime, a standardized no discard attribute to make sure all of our air handling constructs are properly used. We have those off-the-shelf constructs for fitter, alarms, with extensive conditions and responses. Encore also supports reintegration, either at the application level or at the flight computer level. And this behaviorally deterministic execution model I keep harping on, it itself is configurable and customizable, meaning things like Byzantine fault tolerance and other redundancy schemes can be designed modularly rather than as a simple, single, rigid, all-in-one package. Now, the software components are only one part of the safety picture. Underlying Encore is a rigorous software development process that incorporates many facets of NASA's software safety standard. And that process is called Commercial Class A. Commercial Class A achieves the rigor of NASA's Class A human-rated software with far reduced overhead. Think intensely agile. The diagram there on the left is a simplified view of it. The important thing to take away is it's a very tuned, iterative process with multiple feedback loops, incorporating use cases, peer reviews, integrated testing, and test plans. And all of those accessible and easy to use comprehensive tests are done via our stage ecosystem, which I'll introduce shortly. The quality and reliability are enforced through extensive automation, modern software processes, and tools. Our Encore itself was architected and developed to these standards. And any software built with Encore is now enabled to meet those same reliability standards. So I mentioned Stage. Stage is Odyssey's modern automated testing platform for every phase of development and verification. There's a laundry list of features there, and we're going to hopefully showcase those in the demos. But one thing I really want to impress upon you is that Stage itself is flight software agnostic. While seamlessly working with Encore, any flight software framework can work on top of Stage. And if you'll let me be a bit cute, while Encore might be debuting on Stage, anything can choose to go on Stage. But enough of the wordplay. Let's get on to the demos here. So we're going to switch. Some movies come up here in a second. And I say movies because we do have a display outside. we pre-recorded some interactive demos of these things that I intend for you guys to come out and watch. We wanted to be sure that everyone in this big room and everybody online received the same experience. So, how's it coming, Will? That's you? Yeah. Okay, perfect. Excellent. All right, so the first demo is a GNC demonstration. Our Odyssey's guidance, navigation, and control is running on 3 flight computers in a synchronized Encore job, and we're doing one of those R-bar approach scenarios that I mentioned before. Again, think approaching the ISS, but with a little bit more detail. We're going to start with our chaser vehicle, the vehicle that's approaching the ISS about 250 meters away, and then through a series of commanded approaches and hold commands, get to within about 10 meters. Now say, GNC software, this is real GNC. We are receiving sensor data from a simulation, running our navigation column and filters on it, running approach guidance, and our controllers are computing jet firing times. This is the real deal. I can't see it. What's happening here? All right. So the demo, go ahead and fire it off, Will. All right. So one of the features of Stage said was a turnkey test bed. And there you have it. One command line, launching the test bed, starting up all the pieces. Our test bed can choose to cross-compile and deploy your software to hardware, or in this case, we're skipping it, it's already there, and we are choosing to run the R-bar nominal test case, as it's labeled there. The test bed is spinning up flight software, the simulation, the plotting tools, our command and telemetry dashboard, and all of the backing time and data synchronization utilities of the test bed. And just for good measure and eye candy, we're taking the truth data from the sim and rendering it in the Unreal Engine. Now, this quad screen layout is nothing more than us trying to do some amateur video editing to show you some of the neat features. Stage does not force you into this layout. Now, that test case, R-bar nominal, what do I mean when I say test case? Before automation, if we were going to test our flight software, somebody would sit in front of a screen and have to look at telemetry and go, this looks okay, let me send a command. They send a command into the software, then they examine the telemetry. A human in the loop slows it down. Our interactive and automated test bed system allows you to script your test cases. If you know Python, you can write a test case. And with Python comes things like inheritance, which means you can reuse and build on top of test cases easily. Meaning, an entire mission scenario can now be incorporated into your continuous integration system. Very, very, very useful. All right, I mentioned that we're running 3 computers. This is actually a view of our display right outside. These are 3 Korea KR260 robotic starter kits. They are running stock Xilinx Linux, no modifications whatsoever. And I believe it's an ARM architecture, Cortex A53. And I said we were running real GNC. This is actually a view of what one of our Kalman filters looks like consuming Encore. So all of those state machines, all of the alarms, all of the air handling, all of that allowed our developers who were porting old GNC code from C to better test their software and better reason and understand what was going on. So we're actually going to come back and forward ahead now in the scenario a little bit in time. And that's a good time to actually talk about time. I mentioned before that timing was one of those interfaces that we could customize. Normally, an R-bar scenario like this takes on the order of hours to go from 250 meters out. So if we were running our software with timing with the real clock on board, this movie would be 2 hours long, and you guys would throw fruit at me to get me off stage. By divorcing the concept of time from the real clock and instead having it obey a simulation clock, we have unlocked the speed of the software to run, in this case, based on hardware limitations, about 3 times faster than real time. So now this movie would be about 30 minutes, still too long. So that's why you're going to see us jump around, and you might even see the video playback get a bit jerky, just trying to give some context there. So while that telemetry is ticking down, a little bit, a highlight again of what's happening. Each of the 3 flight computers is receiving data from the sim. They're computing their solution and sending it to another box downstream that's doing voting. The voting telemetry stream is being displayed also in our telemetry dashboard there and being piped to the simulation, which is feeding the graphics. Now, we've been kind of ignoring the plotting tools down there. Let's look at that a bit. These plotting tools have access to any telemetry stream in the testbed. They can be web-based, they can be hosted locally. They can run on live data, as they're doing now, or they can run on post-process data. You can overlay post-process data on top of live data. You can do 3D plots. You can search for variables by name, by regular expression. All of this is, time alignment is there. So if your data is time-stamped, we can make sure that you can causally reason about your system and your test case. This is all there to make use and help the developer and the tester reason about their scenario. Now, what about that command and telemetry dashboard? We're trying to automate as much as we can, but there's no reason why you can't use this thing like a traditional operator display. We can actually send in a command. In this case, we sent in bad sensor data intentionally. We injected a failure into one of our computers. Computer went down, the remaining two computers and Encore detected the node went down, and the scenario continues. This drop-down menu on the left here is illustrating our drag and drop telemetry points. And this is the cool thing about Encore, an opt-in feature, if you will. Any data field registered with the data model is immediately accessible and tied to the telemetry system. So if there's something, if a developer took the time to create a data field, you'll be able to look at it in telemetry without having to rebuild, rerun. All right. So now we've skipped ahead towards the very end. And some of you might be wondering, we have 3 separate flight computers. They're talking to the sim. And I said it was a synchronized Encore job. So what do I mean by that? Because if they're really getting their timing from the sim, how are these things remaining synced? Well, again, another configurable part of the Encore execution, these 3 computers are every tick, so let me use that term loosely, sending a message to each other, a gate, if you will, making sure that they're at the same tick at the same time. So this is another form of that behavioral determinism. We're not doing time sync in this example. We're doing tick synchronization. That's a starting place. And this was mostly an excuse for us just to look at how cool the Unreal Engine is as we get close. And we picked the shuttle. We want to play favorites with current vehicles or soon-to-exist vehicles. All right. Now, just because the scenario is wrapping up here, it doesn't mean stage is done with its job. In fact, we can actually just say it's going to work. So what's happening here is the testbed is automatically collecting and post-processing the data from the 3 flight computers. And inside these test cases, the developer has gone to all the trouble to meticulously capture success criteria to deem what is a successful test case. So what we're going to see here shortly is the output from all that to the console. And intentionally, we are showing you all different kinds of things that can happen. It wouldn't be cool if it all just passed, right? You get notifications on pass, fails, warnings. And it doesn't just have to be limited to the console. The testbed is capable of generating automatic reports from this data. So you can see things how test cases map to requirements. You can see how your success criteria rolls up with customized plot support. And it doesn't even have to work for single runs. It works with Monte Carlo sets too. You get information about your dispersion curves, how your success criteria works with pass-fail percentages, and very nice interactive Monte Carlo plots, where if you were able to actually click on one of those trajectories, it could take you to the run in question, and you could further analyze. So there you have it. That is Encore and Stage in a blender in 7.5 minutes, and I'm sure there might be questions percolating, but we're going to roll, in the interest of time, right into demo 2. This one is a much more focused, tight demo on what I'll just call Encore. It's the same hardware, it's hardware that's outside, running much simpler software, and that software is just, we'll say, blinking some lights and remaining heavily time-synced, and we're going to do some cool things like failing computers and bringing them back. Let's bring that up, Will. So I sort of lied. It's Encore, and then we still have our telemetry display. So the viewpoints here, those are our 3 boards in the bottom right. We've got zoom-ins on the top. We've got some LEDs plugged in. And the point of the LEDs is to highlight 2 things. The actual time synchronization that's happening here, and they're displaying a shared job state that is being voted on by all 3 nodes in the job. Now, my colleague actually, as I was blabbering on there, came in and he turned off power to the middle board, node B. And you can see the telemetry has reflected that, the health state of the system, everybody's view. We can see that the 2 remaining computers are computing the same job state and they're voting with each other. And there's also that thing that's called cycle count down there. That's just localized state to each computer. It's merely there to show when a node comes back, we can recover where we left off. 2 different forms of checkpointed data, if you will. Shared across the job and localized to a node. Now, I mentioned before that these is stock Xilinx Linux. So we did nothing, we did no boot optimization or anything. So when you turn these boards off and turn them back on, they take about a minute, which I thought would be okay for this because it gives me time to give some context here. How did Encore determine that a node dropped off? Well, that's another opt-in feature. You can turn on health monitoring for all the nodes participating in a job. When the node finally comes back, he reaches out, contacts the people, he gets information from the nodes he's contacting about the state of the world, and he reintegrates. And right as I said that, my colleague went and failed 2 of the nodes now. And this is a little bit different. I mentioned tick synchronization from demo 1. Well, now I'm mentioning time synchronization. Another configurable policy or interface that we've used here is a time skew. Whenever node A is in the job, he's deemed the master. And nodes B and C can skew their clocks to node A. When node A went down, B had to detect this and switch over to become the master himself. And then before he had time to tell that to C, C went down too. So I believe my colleague has already rebooted those, so we're going to go through the same process. The big thing to pay attention to here when we, hopefully you guys come by and look at this outside, is really focus in on those LEDs. We filmed these with a high resolution camera, and we're definitely at the resolution of about, I think, a millisecond down there. So, and again, stock Linux. A lot you can do just at the application layer, which is a neat thing. All right, so node A is coming back. Consensus value is updated to 2, so 2 nodes are participating. Node C comes back, now all 3 nodes are back, reintegrating, job state recovered, in agreement. Yay. One thing else I want to drive home here, this entire example was about 90% off-the-shelf Encore components. The remaining, what I'll call light customers doing their own implementations, is about 100 lines of code. So there's a lot of pieces for you to build on. So together, Encore and Stage enable rapid yet rigorous development, testing, and deployment. And Brian Rishkoff's here. Encore is available now. Please come by our booth for more information, and thank you.
Questions from the room? Let's start over here.
Hey, thanks. Can you speak a little more to what was happening with the state recovery and how you were picking up state again on reboot?
In the second example?
Yeah.
Yeah. So, sorry for the poor introduction. There were 2 forms of state there, the one localized to the node and the one being shared. So every tick, the job state, the one that's being shared, we are exchanging our view of that state with all the other nodes in the job and performing a vote. So when we come back online, we get the voted information for free from what the outside world is. And then we are able to deduce it. We're making a computation locally, and we compare our local value with the voted answer to get us started. And then after that, it's just mostly a majority rules. The localized state was just demonstrating that you might have something that you don't want to share with other nodes in the job. So there is an application interface, we call it checkpoint dispatch, that lets you implementation define where you want to stick your data. In this case, we just wrote it somewhere and reloaded it on boot.
Thanks.
Great. I think there were some online questions.
Yes, there are. The first one is why C++ and not Rust?
Perfect. I love it. Thank you so much. So, not starting a language war. I do believe modern C++ is very good at listening to the rest of the language community. And if you look ahead at what the Standards Committee is doing there and the work that Herb Sutter is doing in terms of making a newer front end to C++ to be safer, we're seeing what Rust is trying to do. Believe it or not, the air handling framework that's inside Encore is very Rust-like. It is very much like a Rust result. And that's, to no surprise, that's where the C++ standard went with standard expected in C++ 23. So we're all in this together.
All right, I got another one. On one of the slides, you had serialization. How do you handle serialization? And a follow-on specifically for ground telemetry commands. Do you adhere to some industry standards like CCSDS, or is there some Encore tooling needed to serialize telemetry?
The broad answer to that is yes. So when we say serialization, we have, again, this concept of a serialization policy. So some of the off-the-shelf pieces we have is for you the ability to get byte pack serialization, to do byte swapped byte pack serialization. If you know you're on the exact same architecture, same CPU, you can just do what I call identity serialization, which is a mem copy. Now, if you're talking with a ground system or talking to someone that's not C++, you usually need to get something else involved. We can talk about it outside, but some of our application layer code that consumes Encore at Odyssey, we're using flat buffers, for instance, as a way to define the schemas. But within the Encore software itself, within an Encore job, you can use all Encore constructs if you want. You have options.
So we have a couple of questions that we can get to. Is Encore currently being used in flight? If so, what mission?
There will be an announcement tomorrow.
All right. And one last one. Can you easily add additional nodes beyond the 3 to increase availability?
Yes.
The short answer or the long answer?
You can add more. So our job description is config-based. And again, a little heuristic example, I guess we can't really show you in our demo out here. When we were doing a customer demo months back, we were using an 8-node job in our lab. And 30 minutes before the demo, our boss came in and said, hey, can you make it 9? And so it's very easy to customize and add in new nodes. Again, all part of the test bed.
Very good. Thank you so much.
Thank you.
Get a hand for Jeff and Will.